we have discussed about graph Ramsey theory. And similarly, we can also consider the Ramsey number for hypergraph as well. So in order to denote the uniformity, let's use this bracket T sign on the as a superscript, so that let's denote this number, capital R to the bracket, round bracket T of K1, K02, KR. Let this be the smallest n, such that in any, edge coloring with R colors of complete T uniform graph. On n vertices, you can always find the monochromatic complete graph of size ki in ith color. There is just I such that the graph with edges of color I contains a complete subgraph. Of course, this is T uniform subgraph on Ki vertices. So that's analogous to the previous setting. We have learned about this in the undergraduate graph theory course. And what we have learned is that we show that this number is finite number. This exists. The argument is basically same as the inductive argument for the graph case. How did we do the graph case? Assuming that you have only two colors, so you take one vertex and then you see whether it has more red neighbor or blue neighbor. You take it, and then now here, so let's say you want to group bound on RKK. And here, what? If this is bigger than RK minus 1K, and you either find the blue monochromatic KK or red monochromatic KK minus 1, together with this vertex, you would get red KK. So as long as this is bigger than that, then you're done. So that is the bound that this is, technically this is like RK minus 1K plus RK minus 1 plus 1. And similarly, for hypergraph, you could do the similar way. You take a one vertex, and then here what? You consider this vertex set, which is like, you can consider it as one uniform graph. And vertex set, one uniform graph. You partition the one uniform graph into two. Now what? You say you consider the three uniform hypergraph. Then you consider all the edges in here. Meaning that if you have this triangle, so this hyper edge is red, and this hyper edge is blue, and this hyper edge is red, then you consider the coloring on the edges here. That give you a edge coloring here. And if this size bigger than, say, two uniform Ramsey number of, say, three uniform Ramsey number of K minus 1, K, and three uniform Ramsey number of K, K minus 1, then you could find the Let's click of size what? A list this. Then what happened? Then this set W together with this. What do we know? No matter what hyperedge we take, which contains one vertex here and two vertex here, it's always let. And from our choice, this has size bigger than that. That means you can either find the blue KK, or let KK minus 1. And in this case, we are done. In this case, together with V, we are done. So you get like this bound. So that's the inductive bound. You generalize this argumentful graph. And that yields the following bound in general. So if you consider T uniform Ramsey number, then you take T minus 1 uniform Ramsey number, and then each component here, each component in this function is also Ramsey number with one smaller in its coordinate. The last one is like K1 to K R minus 1, KR minus 1. Okay, but how good bound it is? We know that the R2, the 2 uniform KK is at most 4 to the K. Then from here, what do we know? If you repeatedly apply this, then what? This is exponential of this number. And this is another exponential of R3 of say, K minus 2K or K minus 1K. So it's repeatedly, you have to take the exponential function. So what you will see is that the bound you get is like a tower function. And then that the height is like some constant times c. Constant times k. Okay, that's already bad enough, but what if you take a ball uniform? Then this is what? This is tower function because the R3 is tower function. Here you have to take R3 4 tower function. Then the length is what? Length is again R4 of K minus 1K, and this is also, you keep repeating. This is what? The height is also tower function, and then height of this is also tower function, and height of this is also tower function. You have to do this K constant times K times. But this is something called Wouter type function. And that's already 4. 5, 6, 7, you will get like Ackermann type, ridiculously large upper bound. Okay, but would it be true? Would it be necessary? Actually, it's not. So Erdős and Lado found a better upper bound. So Erdős and Lado in 1952 found a better upper bound, say for TLS3 and RLS2, and say K1 to KR are all bigger than T. We have, these assumptions are natural. The T uniform Ramsey number is essentially exponential of the one less uniform Ramsey number. So this is a binomial function. You take the t-1th Ramsey number with one less numbers on every entry of this. Then you take a choose t-1. That's binomial function. But this is like n to the r divided by, essentially like it's n to the r times some constant. But this is the one less uniform Ramsey number to the t-1, and r is also a constant. So before what? Every time you do that, you have to take the Ramsey function again. But instead of Ramsey function, you take the exponential function. And if you repeatedly apply this, then what you get is like for three uniform case, it's this type, the power function, but the height is reasonable. So power function of height 3. Now I'm a bit confused on how I define the height in the previous lecture. When we deal with the regularity lemma, we defined height, but we define height of this as 2 or 3. But let's say it is 3. There are 3 entries. Power function of height 2 is exponential. Let's say that. Anyway, so you have this, and in the similar way, you can show that this is for T uniform. This is the height power of height T, where the biggest one is like some constant times K. And in general, if there are more than 2 colors, the last one is, instead of CK, you can just write constant times RK log K, log R. This log R is here because of this. This is same as like you replace it with 2 and then you write log R on the out. Anyway, this is still quite large, but this is much better than this type of function. This is tower, where the height is also tower, and then height of that tower is also tower, and then height of that tower is also tower, height of that tower is also tower. You have to repeat this, constant K time, which is even difficult to imagine. Yeah. Okay, let's prove this. And we will prove this for simple case when T is for 3, and then there are only 2 colors, and then let's say K1 and K2 are same as just K. And if you understand the proof, then you can simply write the proof for other values. So proof idea is same, so I will just focus on this. So this proof idea is called the stepping down argument. So how do you do it? You assume that you have a coloring on your 3 uniform hypergraph, and you will stepping it down to a graph coloring. And in that graph coloring, you find the clique, and then you transform this clique into a 3 uniform clique. In order for this to be possible, you have to choose the right way to step down. Of course, if you have a coloring on entire V on the 3 uniform hypergraph, you cannot just replace with the edge coloring or the graph coloring. How you should do it is that instead of taking every vertex, you delete many vertices, and in this subset, you consider a graph whose edge colors reflects the 3 uniform hypergraph edge coloring, hyper edge coloring of on this W. So that's roughly the plan. So let R be the graph Ramsey number of R, K-1, K-1. And then let N be the 2 to the 1 plus R choose 2. And what we have to show is that if you have a arbitrary red-blue coloring of the complete 3 uniform hypergraph on n vertices on the, say, vertex set B, we aim to find on edge coloring of some auxiliary bipartite, auxiliary graph G on the some vertex set W, which is the subset of B, whose edge coloring contains full information about high restricted zone W. So in this subgraph, so how do you do it? So we want to take W1, W2, W3, n vertices. And how do you want to do it? And what do you want to do with this? That we want to find some coloring pi prime on the pairs. Coloring on the pairs Wi, Wj. But what do you want? If I prime Wi, Wj with, say, I is more than j is red, we want to make sure that the pi Wi, Wj, Wl is also red for all L bigger than j. So recall that this one is hyperedge coloring, all triples are colored, and this one is graph coloring, pairs are colored. So that's our goal. We want to find such a coloring that if this is red, then this is red. In here, if you find the graph click, so say triangle, no, not triangle, let's say graph click, like K5 or K10, then that vertices, because this is red, every triple there is also red, right? So now what we can achieve is that if we find the monochromatic graph click in here, that gives us the monochromatic hypergraph click in here. So how do we find this? Essentially, we do it inductively. So when you find a certain subsequence which satisfies this condition, and then there are some candidate vertices, then you choose one additional vertices that can extend this while the candidate set shrink. So we can maybe write it slightly more fancier way instead of just writing as a inductive, manner. We take a maximum M and set W, which consists of the, say, W1 to W2, W2 to Wm, and red blue coloring pi prime on the pairs Wi, Wj with I, J are between 1 and M. And vertex set U, which will be the candidate for our next choice, that satisfying the following property. So what's the property. For any I and j, and say third, you take a vertex u, which is either wj plus 1 to wm, or it could be a vertex in u. You don't care. What we have is that this pi prime wi wj is same as pi wi wj u. You see? So our property that we want to satisfy is that if this is lead, we want to make sure that all the triple here is lead. And this also holds for these vertices in U. So that kind of shows that, tells you that this U are candidate to be added as Wm plus 1. Yeah, if you want to add one more vertex, then that vertex also satisfies this property, right? So U is the proper candidate vertex for us to add. And this candidate set has at least n over 2 to the 1 plus m choose 2. So it's not too small. Okay? So we take such a choice. Out of all such a choice, we choose one choice that maximizes m. There could be multiple choices of w, u, and but for each and I prime, and for each of them, you write down the value of m, the size of this w, and you choose one of them which has the maximum. Then we can claim, our claim is that if m is actually bigger than r plus 1. Before doing that, we have to check one thing. In order to take the maximum one, we have to show that at least one such choice exists. It could be empty set. There could be no such choices at all. But that's not the case, because if we just take the w as an empty set and u as not empty set. Let's say this is just one vertex. Then u is everything except one vertex. So this is arbitrary vertex, w1. Then what happened? Then m is 1. This falls, right? This is 0. So it's n over 2. I mean, u had at least 2 vertices. So, I mean, v had at least 2 vertices. So, I mean, this inequality holds. And first one also satisfied. It's vacuous. Out of one vertex, there is no way that you can choose two distinct ij between 1 and 1. So, it's vacuously true. So it satisfies with m equal 1. So there must be such choice, and maximum choice is at least m at least 1. Moreover, we claim that the maximum is m at least r plus 1. Why? Suppose m is more than r, more than or equal to r. Then what? Then, what do we assume? N was this. And m is at most r means that the u is not empty. U has at least one vertex. So, suppose that you have such choice. So assume we have such w, I prime, and u with maximum m, but it's at most r. Then what we do? Because this is not empty, we choose an arbitrary vertex. Say wm plus 1 in this u. It doesn't matter as long as this is one arbitrary vertex. Then what? Our plan is to add this to w, but we have to also extend this coloring and then shrink this u accordingly. But we have to choose the coloring well so that we don't have to shrink U too much. For each U, you see, I mean, what do we have to do to keep this U inside of this capital U? What you do is you consider the following tuple of length m. What's the tuple? We consider f of u as the color of wi, w m plus 1, u. So you consider this set of size 3, this hyperedge, then you consider its coloring for each I. So you have u, and then you have this. You have this wm plus 1. For each u, you see the color of this, and this, and this, and so on. So if this is red, and this is blue, this is red, and this is red, this is blue, then f of u is what? Red, blue, red, 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 blue. And now we kind of see what we are going to do. We want to collect all the u which has the same pattern. And then we keep them, and then we delete the rest of the u. And then we assign such coloring as this is red, this is blue, this is red, this is red, this is blue. We assign that to the pairs. So as this f, what means one of 2 to the m possible tuples, we use the Pigeonhole principle. That yields that there exists a vector x red, blue to the m such that if we collect all the vertices in U whose f value is exactly this vector as size at least what U minus 1 because we deleted w sub m plus 1 and then you divide by 2 to the m and you have to take the Shelley. And I mean this is at least actually 2 to the 1 plus m plus 1 choose 2. Previously this was m choose 2, but now you get the m plus 1 choose 2 here. So it was designed to, we choose in this form to match it. So you can, I mean, this is simple computation. You can do that. So we let what? We extend this coloring pi prime by assigning the value for wi, wm plus 1 with the ith coordinate of this vector x. Then these two bullet points, say star and star star, star and star holes with this choice of w and pi prime and u prime. Why? So this first one is easy. When ij are m most m, I mean the original condition already imply. When j is m plus 1, that's the only new pair. But that's already guaranteed by this choice of x and the definition of pi prime. But what? This contradicts maximality of M, because we said that our choice guaranteed that M was the maximum one, but now we found M plus 1. So it's a contradiction, so our claim holds. And you could write this proof differently, that you start from nothing, and then out of this choice, you extend by 1, you extend by 1, you extend by 1. You can do this until you get, no candidate points at all. And then that process goes at least R times. Then, you can just get the same conclusion. Anyway, once you do that, then by the definition of R, we find monochromatic copy of AK in this W in coloring pi prime. Then this yields 그냥 되겠어. Actually, I said it wrong. So it gives you a monochromatic copy of case of K minus 1 in, let's write it this way, this minus the last one. Since, our coloring is an edge coloring of the graph, and then we extend it into one bigger one. So, what? In W, you choose the last one, M. Then what? M is bigger than R plus 1. So even without this, so here you can find the copy of case of K minus 1. Then what? You have a case of K minus 1. And then you add this WM. Then what do we know? This is the last one. So if these are all lead, then any triple, any three things you choose, they form a lead monochromatic hyperedge. So then this is a copy of monochromatic in pi A 3 uniform AK 1 together with W. That shows the upper bound where that we wanted to show. Okay, so as I mentioned, this is argument called the stepping down argument. And it gives us this upper bound. Let's look at is how good is this upper bound. In order to tell that, we have to also obtain some lower bound to see how good this upper bound is. And I will talk about that in the next video.